In this video, we are going to see how the while loop portion of Arduino program works to control a DC-DC converter. So, as we have for any Arduino program, we first have the variables declaration section, that is from here, line 1 to line 5, where I'm just declaring all the variables which I'm going to use in this. Followed by which void setup appears. We have seen the functionality or the lines which should be present inside the void setup in detail in the previous video when we were talking about reducing PWM using Arduino. However, I would like to give a quick over glance of this. Here, pin mode A3 comma input tells the Arduino that my pin A3 of the analog pins named A0, A1, A2, etc. Here A3 is my input pin, so I have to connect my voltage sensor module's output positive to A3 and negative to ground. And pin mode 10 is the output pin. So if you see, interestingly, Arduino has just one input, which is the output voltage from the converter, and it just gives one output, which is the PWM. On system level, that's all it does. So we have only one input, analog input and digital output, PWM output. And these lines have already been explained in the previous videos more clearly. So I will skip these, and the same applies to these lines also. This is for manipulating the ADC, manipulating the clock frequency of your ADC. Coming to the main part, this is our void loop. So this void loop function runs infinitely. It runs forever. As long as your Arduino is powered, this loop keeps running forever. So in the first statement, we compute or we calculate the value of output voltage present at the output of the converter, and we store it in a variable called V underscore out. V out stands for output voltage of the converter. That is, this V naught is there. This V naught is our V out here. So we are taking output and giving it to pin A3, and we get at pin 10 we get the digital output, and then we give this PWM directly to the gate driver circuit, right? And I have explained this also in detail in one of the previous videos, where we extensively talk about the ADC conversion of how voltage sensor module is interfaced with Arduino. And this number has also been told why it occurs. It occurs because of 5/1023 multiplied by R1 plus R2 upon R2. It appears because of this ratio. This whole thing simplified gives us mere number. From here on, that is from line number 35 to 51, lies our core part. So first, like any control system, we compute the error first. Error is computed by subtracting V out from V reference. So anyway, error equals V reference minus V naught. That's what we are doing here. Here the output voltage is to be maintained at 12 volts, so I'm giving 12 minus V out. Once the error is computed, then we compute the duty ratio with the help of difference equation. So this is my difference equation. This single equation is nothing but the realization of my integral control. This is my integral controller. So this D is the output of this integral controller, and this is of course the duty ratio. Now again, I have simplified this as a single number. This whole number actually comes from this Ki into Ts into half. This is this number. So whatever Ki you are getting it for your converter, put it here, multiply it with the sampling period or the switching period, and then a half here, because that half is associated with e plus e previous upon 2. Again, we have seen with great depth about this difference equation in one of our earlier videos. So this is just assembling of all the concepts which we have covered earlier. Now, once your duty ratio is completed, once your duty ratio is computed, you have to make sure that it does not shoot up to any absurd value. It has to be saturated. That is, if the value computed by this equation exceeds 7.5, you should hold it at, sorry, if this duty ratio exceeds 0.75, then you should hold it at 0.75. Technically, it should be 0.75. You should hold it at 0.75. So if it is exceeding 0.75, hold it at 0.75. Don't allow it to exceed further. So I am saturating the upper limit. Similarly, if the duty ratio goes below 0.3, I am holding it at 0.3. So I am saturating it at the lower limit as well. So this section takes care of duty ratio saturation. Now my duty ratio is ready. It's a mere number lying between 0.3 and 0.75. It is a decimal number. Now I want to make this produce a PWM for me. So I am typecasting it. This process is called typecasting. I am typecasting it and storing it. And this process is also explained in one of the previous videos, where we have seen how the duty ratio, which lies between 0 and 1, is to be scaled between 0 to 800. And why 800? Even that we have seen earlier. So this is basically the number of steps your sawtooth is going to have. This is going to be your sawtooth's amplitude as well. So if this is having a value of 0.3, then it should be 0.3 into 799. So this may not be a perfect whole number or an integer. For that matter, we typecast it. When we say unsigned integer 16 underscore t, it's a template provided by Arduino. So this data type will help you to convert this fraction value into a 16-bit integer. So then we store that integer into this register. Why are we taking so much pain to convert it to a 16-bit number? Because OCR1B is a 16-bit register. So we first convert that duty ratio multiplied by the amplitude of sawtooth, and then convert it into a 16-bit integer. That is, by typecasting we convert it into a 16-bit integer and then store it inside the register. So this will go directly and store inside OCR1B. Here OCR1B will now have a 16-bit number, which will represent your duty ratio, right? Once this is done, this is your OCR1B, and OCR1A is already declared earlier in this stage. Now OCR1B and OCR1A together will produce your PWM. This top value is stored in OCR1A, which is 799, and this duty ratio value is stored in OCR1B, and this will produce you a PWM like this. We have seen about this also in one of our previous videos to a very deep level. And once all of this is done, I have to store the current value of duty ratio and error for the next iteration. So I'm storing this D in a variable called D previous, and I'm storing this E in a variable called as E previous. Once this is done, it will go up. It will go up, read the next sample from the output of the converter, come inside. Inside the Arduino, all the lines of this void loop will be executed. Once it reaches the bottom, it again goes to the top, and it will read the next sample, and this happens forever. The main point here is, I have already told you one of the common and best practices is to take the sample of V0 at some time interval, and that time interval should be your switching time interval. We are talking about a converter whose switching frequency is 20 kilohertz, therefore the switching period is 50 microsecond. Therefore, at every 50th microsecond, it must take the output value, do all the computation, reflect the PWM here, and at the next 50th microsecond, you should take this and do all the stuff. So what does it mean? It means whenever this Vout line is, this particular line is running in the Arduino, it is executing analog read. So whenever it is executing analog read function, it is taking this value, absorbing it, then doing all the computation. So there will be some time taken by the microcontroller to execute each of these statements one by one, and then it will go to the last, and then it will come to the first again, and then it will read the next sample. So what is the point here? The point here is when I'm saying that I should take my output sample at every 50th microsecond, I'm saying that the time taken for the microcontroller between two consecutive analog reads must be 50 microseconds. Let me repeat. So when I'm saying that I want to take a sample at every 50 microsecond, I mean to say that I have to execute this analog read function every 50th microsecond. So the time taken by the microcontroller between two consecutive analog read functions, first time it will execute analog read, it will do all these things, adjust the duty ratio, produce a proper PWM, then come again to the top, and then when it comes to the next analog read, the time gap between consecutive analog reads should be 50 microseconds. But will it really happen? That's the question. Will it really happen? If your microcontroller is extremely fast, all these statements may get executed within 2-3 microseconds, and then you'd have to deliberately delay your loop by writing delay microseconds function for 47 microseconds. If this from here to here, if it is taking 3 microseconds only to compute, then you have to further delay it for 47 microseconds and match to 50 microseconds so that next time it will go up here. So here playing with time is very important. So let us first observe what is the time taken by the microcontroller between two consecutive analog reads, or what is the time taken by the microcontroller for executing this while loop one time. For once executing this while loop once, let us first find out what's the time it is taking. If it is taking 50 microseconds, well and good. If it is not taking 50 microseconds, we have to see what to do, right? So the story here is, if coincidentally, if this is taking exactly 50 microseconds, I need not worry about anything. I can just deploy it and finish my work off. If it is running very fast, assume that it is doing from here to here, the entire loop within 10 microseconds itself. Then I have to deliberately introduce a delay here of 40 microseconds so that it will take 10 microseconds for computation, waits for 40 microseconds, and then again goes up. Now, the problem is, if this is taking more than 50 microseconds, then what will happen? So you may not be able to take sample at every 15 microsecond now. Assume that you are able to take the sample only every 80th microsecond or every 85th microsecond, something like that. If that happens, what's the scenario? For that, as I said earlier, first we should find out what is the time consumed for running the loop one time. So there are two ways for this. The first way involves using a CRO. The second way doesn't involve using a CRO. However, the CRO method gives you more accurate value of the time. So if you are having a CRO with you or a DSO with you, please use the method 1. Let us explore what's method 1. Method 1 conceptually goes like this. So this is a while loop. You are having analog read function as the first line, and then you are having some lines, forget about those, At the end of every infinite loop, that is after this last line, that is after this, let me erase this delay microsecond. After this last line, you have to toggle your sixth pin. Toggle your pin 6. Why pin 6? You can take any digital pin for toggling. I have already used pin number 10. 9 and 10 are associated with timer 1. So other than that, I have to take some other pin. That's it. That's a simple reason. I am taking pin 6. Fine. Now just toggle it. When you toggle it, what will happen? When you toggle it, the waveform which will come out of pin 6 in your Arduino will look something like this. This is your pin 6 or D6 of your Arduino, okay? You are connecting DSO across pin 6 and ground of your Arduino. Let us assume this case. You are measuring the voltage or connecting a DSO, a scope basically, across these two pins. Here's your probe, and then you are connecting it to a scope, and then we are viewing the waveform here. How will the waveform look like? When I am saying toggling means if my pin 6 is having logic 1, it should go to logic 0. If it is having logic 0, it should come to logic 1. That's the meaning of toggling. So initially the pin may have some value. So when the loop runs one time, if I'm toggling it, it goes from 0 to 1 and then stays at 1 itself. This compiler will go up again, it will execute all the statements. Again, when it comes to last line, it will toggle. So what is available now? Logic 1 is available. Logic 1 will go down to logic 0 and it will stay at logic 0 itself. Again, when it goes up, it will read all the lines, execute all the lines, and then come to the last line and then again toggle it. So it will go up to 1 and stay at 1. So what does it mean? This means that this time is my loop time, loop runtime. So this is one idea. So, but how do you toggle this pin 6? You can, or you should use port manipulation. Don't use any other thing, any other code, because that itself will consume some time. So use port D XOR equals binary. You might have to use 0 1 0 0 0 0 0 0. So I am not going to cover what this statement exactly, how the syntax of the statement works. This is a XOR function. I can tell you up to that level. And when I'm saying port D, Arduino, as you know, has several pins. In that, port D has from D0 to D7. These 8 pins come under port D. So when I'm saying port D XOR equals something, this first bit corresponds to pin number 0, second bit corresponds to pin number 1, third bit corresponds to pin number 2, fourth bit corresponds to pin number 3, and so on. Last bit, 8th bit corresponds to pin number 7, 7th bit corresponds to pin number 6. When I'm writing 1 in the 6th bit, that means pin number 6 will toggle everything according to this particular function. If you want to read more about this function, you can read it. So this is one idea how to do that. So at the end, you will get a waveform like this. So in your CRO or in your DSO, you will get a waveform like this. Observe one thing, that here 1 unit equals 50 microsecond. My on time and off time is constituting me or giving me how much? 100 microsecond. That means what? It means that it takes 100 microseconds for the while loop to run once, which is twice that of my switching time period. Now this is a challenge. I want to explain you this so that we can cover stability analysis as well. So this exactly happened in my case when I was working with the hardware. So this entire thing takes 100 microsecond to run once, so which is twice my switching time period. That means it will take sample not at every 50th microsecond. It will take the sample at only every 100th microsecond. I will miss all the data in between 100 microseconds. So is that fine? That's a question. We'll try to answer it. The second way to compute the time consumed for one iteration of the infinite loop is by using micro s functions. There is something called as micro s. It's a function. What you can do is in this, at this area, you can write t1 equals micros function, and then again here you can use t2 equals micro s function, and then here you can use t3 equals micro s function, and so on. Wherever you want to introduce some timestamps, you can introduce micro s functions in those places. This micro s function, this microsecond function, basically it will tell you the current time of the Arduino, which is going on forever in a particular long register. It will keep running forever. It will capture that value and store it in T1. Again, you are doing something. There will be some time delay. Again, you are using this micro s function to store it in a value called T2. Now, in the end, if you do T2 minus T1, what will you get? You will get the time consumed between these two micro s functions. That is nothing but the time taken to execute all the statements present between these two micro s functions. This is one way. But there's a disclaimer here. This may not be as accurate as you think, because there are some limitations when you're using this. So try not to use this. Try to use this method. If you're not having a DSO in your hand, and if you're having only Arduino, then you can go for this method. So at the last, you can just type serial.println of t2 minus t1 minus 4. Whenever you are subtracting two micro s functions, always subtract a number 4 from it also, because as per my observation, when I'm executing two micro s function back to back, and if I am printing t2 minus t1 in my screen, it should technically show 0, but it won't show 0. It will show 4 microseconds. So that 4 microseconds is basically taken for running this micro s function itself. So that's the implicit meaning of that. So always do this. With that, we can conclude this topic, and we have figured out how to compute the loop delay, or the time taken by the microcontroller for making the while loop run once. Now the question is this going to be a problem? If my runtime is more than, or if my sampling period is more than the switching period, will it become a problem? We have to conduct an analysis for that. We'll see that in the next video.